So in our last video, we talked about states of matter and phase diagrams, and I want to just take a little bit of time here to talk about vapor pressure, which is a fairly critical point to understand. Boiling, which I think is probably a fairly misunderstood process. So vapor pressure. So here we have a sealed container with some liquid in the container, and under those conditions, you're going to generate an equilibrium of some particles of that liquid are going to vaporize into a gas. And this is in part due to the fact that the temperature of any substance is the average kinetic energy of particles in that sample of matter. And so some of those particles have a fairly high kinetic energy relative to the average, and they can escape the interparticle forces that hold that liquid together. At the same time, some of the vapor particles that are above that liquid are going to be moving slow enough that when they get near the liquid, they're going to recondense back into the liquid. And so what we get is um, we get this layer of gas, if you will, above the liquid in this sealed container. And as those gas particles bounce around, they exert a pressure on the surface of the liquid. And we refer to that as the vapor pressure. It's the equilibrium pressure of that vapor that is above the liquid. Or if you're below the triple point and you have a solid that is turning to a gas that is subliming, then you can have a vapor pressure above the solid. So it's fairly easy to describe that in terms of a sealed container. But what happens when you have an open container? So here we have a beaker which has some liquid in it. And so in an open container, what you get is the atmospheric pressure above that beaker is going to create to some degree the seal, but of course that seal is not airtight, and so some of the vapor particles above that liquid are going to have enough energy to escape that atmospheric pressure, and this of course is how you get evaporation. And I want to specifically now talk a little bit about the difference between evaporation and boiling. So at any temperature of a liquid, some particles, again average kinetic energy, have enough energy to escape the liquid and go into the vapor form. But that only happens across the surface of any liquid in an evaporation process. And when that is taking place, it's taking place below the boiling point. And the reason for that is that below the boiling point, atmospheric pressure is going to keep any bubbles from forming inside that liquid. So only fast-moving particles on the surface can escape the attraction of the liquid particles and evaporate. Most of that gas, of course, though, below atmosphere or when you're below the boiling point, hovers and creates a vapor pressure above that liquid. Boiling, on the other hand, happens when the temperature gets high enough that you can create enough kinetic energy to start forming bubbles inside the liquid. And the key feature that's going on there is that the pressure inside those bubbles is temperature dependent. So below the boiling point, bubbles cannot form and sustain because the atmospheric pressure above the liquid is going to cause them to collapse immediately when they try to form. But as the temperature gets higher and higher, the pressure inside that bubble can sustain against the atmospheric pressure pushing down. Essentially, the pressure inside the bubble is equivalent to the vapor pressure, and when it gets greater than the atmospheric pressure, you can have bubbles forming throughout the liquid and you get boiling. So again, evaporation is only a surface process. It happens below the boiling point, whereas vaporization or boiling happens when that vapor pressure is equal to the atmospheric pressure, and those bubbles can then form and liquid particles can escape and become a vapor. And so when we look at this relative to the phase diagram, of course, we see that the boiling point can change rather dramatically with pressure, and you can actually boil water fairly near the freezing point if you get the pressure low enough. If we move up a little higher here at about 10 kilopascals, which is about 1/10 atmospheric pressure or zero point 0.1 atmospheres, you can boil water at 50 degrees Celsius. And so there is this kind of assumption that boiling is a function of things being hot, and yet you can actually boil things at fairly low temperatures if the pressures are low enough.